Hello, and to whoever who is watching this video, welcome to my channel. And I hope you are ready to solve another lead code question today. The question that we're going to do today is this one, LC-416 partition equal subset sum. So again, as I said in my previous video, I will not waste much time reading through the question. We'll directly jump to the examples, understanding the input and the output, and then we'll look into the code. We'll do it using two approaches. First, the normal approach, and then we would optimize the solution to pass all the test cases. All right, so let's get started. Okay, so basically, we are given an input array, an integer input array nums, and we need to return a boolean. In what case? In the case when the array can be divided into two subsets, such that the sum of the elements of these two subsets is equal. So what does this mean? This means that, let's say, if my input array is this one, let me just paste it down. Can I partition this array into two parts such that the sum of the elements in one subset and in another subset is equal? So let's see if we can do that for this input, right? So let me write down it as, let's say, 1 comma 5. Sorry, 1 comma 5 and comma 5. This sums 11, right? And the remaining element is 11. So that means one such partition is possible, right? So 5 plus 5 plus 1 is 11, which is equal to the remaining element. So that means this partition is possible. So in this case, my output is going to be true, right? And if we look through the second example, 1, 2, 3, 5, which is given to us, let's see if we can do this. So basically, if you think of it, you can also think of it in a way that if I sum all the elements, 1 plus 2, 3, 3 plus 3, 5, 3 plus 3, 6, and 6 plus 5, 11. So is it any way possible to divide the array into two parts such that the sum of both of these is equal? Can we do that for odd numbers? Actually, you won't be able to do that, right? Because it's an odd number. So in any case, when I'm given an odd number, I can simply return false because I know 11 by 2 is 5.5, and I cannot get that sum from my any subsets of my array, right? So in this case, I can simply return false. Okay, so even in this question, you can think of it this way, that you are given 1, 5, 11, 5, and if you sum all of these, it would be 1 plus 5, 6, 6 plus 11, 17, 17 plus 5, 22. So 22 would divide by 2 is 11. So you need to find like one possible partition for that array such that the sum of each of this is 11. So in this case, you are able to find it. Some cases you might not be able to find it, and in some cases you do not have to even try finding it when it is an odd number, right? So actually you can break down the problem into finding the solution such that does that subset exists in the array or not, whose sum is 11, or whose sum is the total sum divided by 2, because you know that since the target sum that you have to find is the sum of all divided by 2, that means whatever one subset that you have found, the remaining subset of the array would also be equal to the same sum, right? So that's like the crux of this problem, that you can break it down into a simpler version like that. So let's start going towards the solution, how we can write and approach it in Java. So what I'll do is I'll make another function. Let me write it down. Now, in this, what I'll also need to know is like keep track of whether I have covered the current index or not, right? So I'll keep one int I, and as I just talked about, that we need to make sure that we are also targeting a target sum which we have been able to find or not. So I'll also keep a sum value. Okay. Now, how will this sum be decided? So let's see, as we just discussed, we'll have to sum all the elements and then pass the half of it. So for that I need to basically get the sum first for all the elements. So I'll use fast iteration for arrays, and let me also declare an variable sum and sum it up, right? Now, one check that you can do right now, right here, is that if this number is odd, you don't proceed to do anything, because in that case, you cannot find any partition that can return you, that can be returned to you from the nums, right? So, only in the case when it is an even number and you are able to divide by 2 completely, you can go and try to find that partition, otherwise, you won't be able to. So, what I can do is that if my sum modulus 2 is equals to 1, that means this is an odd number. That case, just return false. Don't need to do any check. In the case when it is not, what you have to do is call this function, the helper function, and you have to actually write your logic to find whether you are able to find that partition or not. So in that case, what I'll do is I'll return can partition, and the index that I'm going to start with is 0. Okay, and now the sum would be divide by 2. Why it is divide by 2? Because again I'm repeating that you have to sum all the array and you have to divide it into two parts such that the sum of these two are equal. Now in what case can the sum of two be equal? In the case when the total sum of them is equals to the sum of all the elements, right? This is the only point that you need to understand. Okay, and that is why you have to pass half. And if you are able to get the sum, like get a positive true result for sum by 2, then that means that the remaining subset that you have to, that you did not consider, would be also sum by 2, and so it will return you the result. Okay, so that is the point that you need to understand. Okay, and so now when we have passed index, when we have passed sum by 2, and when we have added nums also to the parameter, let's see what we'll do in this question. So, what would be my base cases? My base cases would be that, since I'm starting from the sum, so when I'm able to, like, get all the sums and I have reached 0, that would be the point that my base case would be hit, right? So what you will keep is, you can keep sum. If it is equals to 0, then that means you have been able to find one such subset, right? So you'll return true. Now, in the case when your sum has not been able to reach 0, but you're continuously decreasing it, right? In that case, it would be less than 0. And in that case, you have to return false, that, partition is not found. So, sorry, return false. Okay. And if you've not understood this base conditions, just wait for 1 minute. You will understand it when we walk through the recursive calls, right? Now, how will the recursive calls look like? Basically, I'll have to make recursive call twice. One is that you can partition, you are going to consider this current element, and that is why you will reduce the sum. Okay, to keep the nums. This is the case when you're considering the current element to be part of a possible subset, right? Another case is that uh, you are not considering the current element. In that case, you are going ahead, but you are not considering it to be the part of the sum. So that's why I do not have to decrease my sum. Now, in any of these two calls, if I get any one possible partition, then I need to return it, right? That is why the relation between these two would be an OR relation. That's why I want to keep OR. Okay. Now I'll have to return this. Oh, I hope you have understood this. That in this case we are considering the nums, and in this case we are not considering the current nums I. Okay. Now, one more thing that you need to understand here is that sometime it would be the cases that none of these two conditions are matched, but your index has gone past the current nums array, right? So you need to take care of that, and that is why this condition, that if my I has gone beyond the nums length, that is I has become greater than or equal to nums dot length, then in that case also return false, because this becomes an out of bound condition, right? So you do not have to consider calling another recursive call in that. So this is the basic first level solution of this problem. Let's see how we have done and try to run it. We've got the nums, we've got the sum, starting with this and nums, then I and some nums. All right, yeah, let's try running it. All right, so to show you the test cases, actually, let's remove these and now try running it. You'll see that the basic test cases, yeah, so the basic test cases got passed, but if I submit it, it will give me TLE, right? Okay. Yeah, so you are seeing that 36 out of 141 test cases passed, and this is a test case that is now giving us TLE. So now what we need to do is basically optimize our solution further so that the TLE part does not come, right? So how are you going to optimize it? Yeah, so we are going to optimize it using a memoization approach, and let's see how we can do that. So in memoization, what I need is I need to basically store these computations, right? And actually, yeah, let's do it in part two because it's going to be a longer video. So yeah, I'll see you in part two if you want to see how I can, optimize this solution. So yeah, thank you. Thanks for watching. Bye bye.